Welcome to In 5 Minutes. The agenda of this clip is to study junction capacitance. In the previous clip, we have already seen the lump representation of the parasitic MOSFET capacitance. In case we have not, then it's very simple. You draw the four terminals of the MOSFET and identify the capacitance between two of its terminals and see which all capacitance are going to be important for you to look into. There would be no capacitance between the source and the drain, because between the source and the drain there will be a channel which will be present and there will be no capacitance. Just remember that. So in the previous clip we have already studied oxide capacitance. In this clip we are going to study junction capacitance, and the two junction capacitance which are left for us to study are nothing but drain to bulk and source to bulk, drain to body or source to body. Both are due to the depletion region charge surrounding the source and the drain. It's basically nothing but this, source and drain. They would have a depletion region charge surrounding it. We already know this through the working of the MOSFET. Ideally, this N and this P of drain and this N and this P, N of source and P of body and N of drain and P of body, they ideally have a reverse bias PN junction diode which is formed for its normal operation. And we know that there is a depletion region which gets created. Here, we are just talking about the capacitance due to the depletion region charge surrounding the source and the drain. So as you keep on varying your terminal voltages, specifically your drain voltage, this depletion region will keep on changing, or the depletion region charge will keep on changing, which in turn will change the value of your junction capacitance, or this capacitance, which is nothing but the junction capacitance. Will come to it, why it's called junction. So these are the basics. Before we go and see this, let's understand. This is a cross-sectional view. Let's focus our attention to drain N-type diffusion. If you see around this drain, there will be a depletion region charge. So it will be the case around the source. So between the drain to source and the substrate, so between your junction and your substrate is a capacitance which you are trying to identify. Drain and source junction and your depletion region, that capacitance is what you are interested in finding. So just pay attention. We are going to just zoom into this N-type and draw a 3D diagram. Here I have drawn that N-type with this 3D diagram. So what I have done here is N-type diffusion region is surrounded by P-type substrate in 3D, and I have indicated all the regions with 1, 2, 3, 4, 5 with the dimensions given as you can see. If you observe this carefully, this area 2, 3 and 4, because this is N-type, right? So there is N present here, N plus, N plus, N plus. But in 3D, they are surrounded by a channel stop implant, which is nothing but P plus. I hope you understand this. See, this N plus is surrounded by P plus, and if you extend it in 3D, you will understand that 2, 3 and 4 are the regions which are surrounded by a P plus region of channel stop implant. So that's exactly, let's see it here. Junction 2, junction 3 and junction 4, N plus P plus, N plus P plus, N plus P plus type. And here is nothing but the area of each junction. Area is width into length. Here it's Y into Xj, so it's written that way. Here it's Xj into W, so it's written that way, so on and so forth. Whereas region 1 and region 5, this is towards the substrate, right? So this has P type N plus type, N plus because it's a diffusion, and similarly junction 1 also has N plus. It's also facing the substrate, so N plus and P, correct? So the substrate, we are assuming that the P-type substrate has a doping density of Na, but the P plus channel stop implant will have a doping density which is going to be 10 times Na. Now when we say this, what's going to happen is that the sidewall capacitance, this we can also call as sidewall capacitance for 2, 3 and 4, they will technically have a different value from the other junction capacitance. But for the time being, we are not getting into that. For this entire analysis, we are going to presume an abrupt step PN junction profile. What do you mean by abrupt step PN junction profile? Here, P and N layers would be uniformly doped with acceptor density Na and doper density Nd respectively. When they both are uniformly doped, this idealized PN junction is nothing but a step junction or an abrupt junction. So we are assuming that for our analysis to start off with. So I think we're all set to do the analysis of junction capacitance.